dimensions.
It's 2 dimensions. Thank you very much. Whoever said that, that's awesome. Yeah, so we're looking at 2D vectors right now, but today we are going to look at 3D. And most of the class is done in 3D, but we're going to go back and forth between 2D, 2 dimensions, and 3D for the rest of the semester. So you have to be comfortable with both, and that's important. So here's a picture of a vector. It's not in standard position because I don't have the initial point sitting on top of the origin. It's just kind of hanging out there. So if you have a point P located with coordinates x1, y1, and a point Q over here with coordinates x2, y2, and somebody says, hey, connect those 2 points and form the vector PQ. So you denote it with component form, angular brackets, and then you take the difference of the x coordinates to get the x component. And keep in mind, order matters. So you want to do terminal minus initial. The terminal point is the one that has the arrow on it. And then the y component is simply the difference of the y coordinates of those 2 points. Okay? Vectors are different from scalars because they have both a magnitude and a direction. A scalar is just a pure real number. Vector notation, when you look at a textbook, you'll know it's a vector because they use boldface. But when you handwrite a vector, you'll give me the name of the vector and you'll put a little arrow on the top. Okay, so last time we did component form, which means
excuse me, Professor?
Yes.
I don't think your screen share is on.
It's not? Oh, wow, that's a big problem. Thank you. Okay, thank you for letting me know. I thought, well, I did it before, right? Okay, how's that?
We can see it now.
Yeah, that's good.
Okay, so we did vectors, and thank you for letting me know. And always please tell me if I don't have my screen share on, because I don't know what's going on your end. And I'm a little verschnagled today because of this whole internet problem that I have in my house. It just makes me nuts. So PQ, terminal minus initial. Vectors have magnitude and direction. Scalars are numbers. Vector notation, component form. Now, if somebody gives you component form of a vector, do you know how to graph it in standard position? You better. So just as an example, let's say somebody said, hey, what's the vector 2, 3 look like? How do you graph it? Well, you actually just find the point with coordinates 2, 3. Okay, so let's say here's the x-axis, there's a 2, there's a 3. There's the point 2, 3. And then starting at the origin here, because that's the initial point, you just draw a little vector, just like that. It's that easy, no kidding. Okay, now once you have a vector in hand, how do you get its magnitude, which is a fancy word for length? So the magnitude, which is denoted with double bars, although Briggs uses single bars, I don't like single bars because it reminds me of absolute value, and that's not what this is. You're going to simply take the square root of the sum of the squares of the components. So this particular vector with components 2, 3 would have a magnitude of square root of 13. Okay, that just gives the length of that vector. Okay, now a lot of times you're going to be asked to unitize a vector. So what the heck does unitizing a vector mean? It means that you are going to shrink or stretch the vector, as the case may be, so it's only 1 unit in length. So the formula is you take your vector and you simply divide it by the scalar, which is its magnitude. So this vector that I had, I'm just using 2, 3, you would divide it by its magnitude and you would get the unitized vector pointing in the same direction as the original vector. What if I said to you, because this is a quiz question, what is a unit vector but pointing in the opposite direction of the original vector? How would you do that?
Take the negative of it.
Very good. Excellent. Excellent. And some other things that we did that I don't feel like reviewing, but you better know how to do because we finished off the lecture last time. We looked at adding and subtracting vectors and scalar multiplication. And we'll do some more today, so don't worry. All right? So that was just a quick rehash of last time. So let's talk about a theorem that's very important, the triangle inequality. I'm not going to ask you to prove this, but if you go on ahead and take a vector calculus class, they might ask you to prove it. And it's not that hard to prove. But the idea is this. The magnitude of the sum of two vectors is always going to be less than or equal to the sum of the individual magnitudes. That's it. Well, what's that got to do with a triangle? Good question. Let's take a look. If you have a vector u, let's say there's the vector u, and then you have another vector v right there. I taught you guys what visually the sum u plus v looks like. Remember, we looked at how that looks like visually speaking? And one of the ways was using the parallelogram law method, which is if you think of these two vectors as being adjacent sides of a parallelogram, the sum of these two puppies is simply the diagonal of the parallelogram. Do you remember that? Another way you could have looked at this to find the same u plus v is you could have translated the v so that he had his tail touching the tip of u, like over here. Here's v. I'm just maintaining his magnitude and direction. And then you connect the tail of u to the tip of v, and that also gives you u plus v. Either way, it gives you the same result. Do you see we sort of have a little triangle right there? So here's a way of thinking of why the triangle inequality works. This is not a real proof. This is just sort of a first grader's addition of the proof. Let's say here's u, and here's someplace you want to go. Well, we can't go anywhere these days, but pretend that this is Southwestern College over here. What's the quickest path for you to get from your house to Southwestern College? Is it along the u plus v, or would it be quicker to go here on this path first and then over here on this path? What's obvious?
Traverse the
U plus V.
hypotenuse.
Yeah, to go, the shortest route is along the u plus v. See that? It's the quick and dirty way to go. Now you could go the long way, but the sum of this magnitude and the sum of this magnitude is going to be greater than or equal to the short route. Does everybody see that? So it's pretty obvious. Now, what about the equality? Because in this little triangle picture I have, this is strictly a less than symbol. That path is strictly less than the sum. When would you have equality? Does anybody want to take a quick guess?
It's like the distance formula, right?
I'm using your charger for a moment, for your charger for your computer.
Using my charger? You guys got to mute yourself here.
It's a pretty long charger.
Get through the computer because I could use a really good internet connection. Okay, folks, for those of you who are just sitting there going, I don't know, or maybe you're just bored out of your mind, I don't know what. Suppose u was this way, and let's say v was parallel to u. In other words, they're pointing in the same direction. That could happen, right? What's u plus v now?
Sum of their magnitudes.
Yeah, it's going to be, from like here's u and here's Southwestern College. Do you see now that u plus v is in fact going to give you exactly the same as the sum of the magnitudes? So it's not really a triangle anymore. We call that a deformed triangle. It looks like somebody flattened it out and stepped on it. Okay, that's the only time you would have the equality. Okay, just good to know. Let's move on. All right, so what's some more definitions and facts that we need? We're going to look at the standard unit vector, and writing a vector is a linear combination of the standard unit vectors. But not yet. Whip out your phones, people.
What?
What?
First.
Okay, what you're going to do once I hit play is you're going to log in using a special number. You're going to go to kahoot.it. Let me write this down. So when you're on your phone, what you're going to do is go to kahoot.it in order to play the game. Okay? And once you're there, what's going to happen, for self-paced learning, here we go. Classic. So you're going to join at kahoot.it, and then you're going to enter the game pin, which is this number you see on your screen, okay? And once everybody's logged in, you don't have to use your real name. I don't even care. Just something family friendly, okay? I don't want to see any horrible, weird names. Otherwise, I will remove you from the game, okay? So be nice.
I just got the I just got the biggest nostalgia trip back to high school. This is great.
Blue octopus.
Okay, we have 28 people in the class, so some of you aren't joining. Come on, you want to play this game. It's just a fun little game. There's just going to be some multiple choice problems about vectors, you know. Penguin, huh? I like penguins.
I think some people are having problems loading into the
But
game.
I'm plugging in. Okay. I don't know much Spanish. What does lechuga fresca mean?
Fresh
Oh
lettuce.
my god.
What?
Fresh lettuce.
Fresh what?
Lettuce.
Lettuce?
Yeah.
Odd. Okay. I'm going to start the game. Are you guys ready?
Yeah.
Oh, here we go.
Get ready.
Oh, Nicholas Gonzalez
Okay.
got left
Which
out.
one of the following fun facts about your prof is false? You're looking for false. She was in a flamenco dance troupe for a few years. She's been to Egypt, Greece, Italy. She has 2 kids. She's certified in scuba diving.
One is too real.
Oh, damn it.
Okay, everything there is true, except I don't have any kids.
I'm in 4th place.
All right. Let's see, what do we have here? Oh, no. How do I get back out of here?
There's an X in the top right.
There we go. I didn't want to do that. So who's ahead? Doesn't it say who's ahead?
You should press next, and I think it does that. Maybe, maybe not.
Oh, there we go. Okay, whoever whose name is Panda got the answer the quickest, okay? And we have some other folks who did pretty well, so congratulations. Let's go on to the next question. Are you ready? Okay, a vector consists of both, and your choices are magnitude and direction, magnitude and velocity, velocity and direction. All right, looks like most of you got it right. Congratulations. Magnitude and direction is what we're looking for here. Velocity is a vector and has magnitude direction, but that's not something a vector has, okay? And speed is basically magnitude of a velocity vector. So that's, speed is a scalar. All right, let's hit next and see who's Panda. Panda is on top. Okay, still. Beans in 2nd place and Big Bob is 3rd. Congratulations. Let's move on. Okay, number 3, what does a scalar consist of? Here you go. Okay, looks like most of you got it right. And so the answer is magnitude only, because magnitude is a scalar, pure number. Okay, let's see. Ooh, Big Bob's on top. All right, Big Bob, Beans in 2nd and Chris in 3rd. Congratulations.
Let's go.
These
All right.
points make no sense, so don't look at me. I have nothing to do with all the weird points that this is Kahoot, okay? Number 4, what's the key difference between vector and scalar quantities?
Bless you.
Okay, most of you got it right. So direction, scalars don't have a direction, okay? They just have a number associated to it, which could be a magnitude, but it could be something else. Okay, wait a minute. Ooh, Beans on top, Chris in second, and Big Bob in third, okay? Nyla, you're doing pretty well. You're always in the top 5. Congrats. All right. Number 5, keep going. So here's a thing here, time. Is that a scalar or a vector? Or neither? All right.
Oh my god, I threw.
That's a little bit tricky.
No!
What was the answer? Sorry.
It was scalar, it was scalar.
It's
because-
a scalar. Yeah, it's a scalar.
There's no direction.
There's no direction of time. Well, yeah, it's always going forward. No, not in my world. I always live in the past, so I like to go backward.
Despite of the
Okay.
theoretical.
Chris and top, Sugma, then Beans. Let's keep going. We got 12 total. Is force a scalar or vector? Okay, most of you got it right. Yes. Well, everybody got it right. Force is a vector. Yay. Good job. Chris on top. No? Yeah, and Sugma
Oh.
second. Beans third. Congratulations. Let's keep going.
Where did Chris come from?
I don't know.
Who is this contender?
Is distance a scalar or vector or neither? Okay, most people got it right. Distance is a scalar. It's just a number. Chris, Big Bob, and Sugma. Congratulations. Chris is now on top. First time.
Where did this
Right.
1,000-point lead come from?
Temperature, scalar, vector, or neither?
Oh, I wish I could take it back.
Nick, you're funny. Relative to your head, it's going to be incoming. Okay, it's a scalar. Most of you got it right. And what do we have when we redo the result here? Okay, Chris on top still. Big Bob and Nyla is in the top 3. Congratulations.
This-
Jordan's up
Threw
and
away
coming
my-
on the 4. Kiana's coming up on the 5. Is velocity a scalar or vector? Everybody better get this right. Come on, peeps. You know this. You know this.
No, I don't want to zoom in. I want to click.
Is somebody not playing? Come on, people. Play the game.
There is one person in chat that couldn't get on.
Okay, you're stuck there. It's kind of
Oh
technical.
my god. Oh,
Velocity is a vector because it's got magnitude and direction. Okay, who do we have?
Oh my
Still
God,
on
a sausage
top, Nyla is
figure.
number 2, and Ant is number 3, followed by Jordan and I Heart Triangulette, whatever that means. Okie dokie. Got 3 more to go. Here we go. Is mass a scalar or a vector? If you took physics, you may know what this is. Mass is kind of like weight, but not really. It's kind of like weight divided by density. Just guess, people. Remember, the points don't matter. Okay, it is a scalar. Congratulations. Chris still on top. Ant now a number 2. Jordan's number 3. I Heart Trianglet and Big Bob. Okay, 2 more. What is this method of adding vectors called? So look at the diagram on the screen before you pick your choice. So head to tail, head to toe, vector to vector, vector to resultant. I didn't mention this kind, but I think you can figure it out. It's one of the kinds I did go over. Yeah, I called it tail to tip, but some people call it head to tail, and that's the method that's shown. Chris still on top with 10,000 points. Big Bob, I Heart Trianglet, Kiana, and Sugma. Congratulations. 1 more, and then we'll have a grand champion. A vector has initial point 3, 7, and a terminal point 3, -2. Find its component form. So here are some possible choices. Which one of those do you think is the one?
Oh, I fat fingered. I think.
Oh, what?
Uh-oh, not everybody got this
100%.
one right, so I must not be doing a very good job of teaching. Folks, it's terminal minus initial. So those of you that answered something weird, the answer is 0, -9. Why? Because you're going to go 3 minus 3, you know, the terminal point minus the initial point x coordinates, which is 0, so most of you hopefully got that right. And then you take the difference of the y coordinates, and you have to do it in the correct order, terminal minus initial. Yes, it matters.
Ow.
-2 minus 7. What's -2 minus 7?
-9.
Yes, indeed. Okay, so please don't blow this, because this is like key. This kind of stuff is going to be on midterm 1, midterm 2, midterm 3, this particular problem, and the final. So you want to know how to do it, okay? So let's see who our grand champion is. Big Bob is in 3rd. Woohoo!
I can't believe.
Kiana, number 2. Chris, woohoo! Runners up, I Heart Trianglet and Ant. Congratulations to all. Okay, so let's get the hell out of here.
How did you know you weren't going to make it in the engineering field? I lost a round at Cahoots.
Kahoot makes me so like irrationally competitive. I don't know. There's probably like subconscious mind
No.
altering like like frequencies of the music.
I think it's just these party games. It brings
You're
out
right.
like an animalistic part of us.
It reminds me of Jackbox, and like that really does like lower your brain
Okay, I
like
couldn't
5
leave the
evolutionary
page for
steps.
some reason. It was driving me nuts. Okay, all right, folks, let's get to real math. I hope you had a little bit of fun and maybe you learned something along the way. All right, let's talk about a different way to denote a vector, okay? So besides the component form with the angular brackets and the comma, there's another way to do it. So first you have to learn a little prep work, and then you'll get to see the alternate way. So there's a vector called I, and the way you're going to do it, I usually call it I hat, and so I use a hat instead of a vector. You could still use a vector. And there's another vector called J, or I call it J hat, and they're standard unit vectors. The word unit vectors, that means they're 1 unit in length. Okay, you should know that already, but in case you forgot. Okay, so these vectors are very cute, and the reason why you care is because in the XY coordinate plane, if I were to graph the I hat vector, it first just graph the point 1, 0 here on the x-axis, and then draw a little vector going. That's the I hat vector. And then J hat, just graph his components as a point, 0, 1, and just draw a little vector there. There's J hat. Those two little guys are 1 unit long. The I hat is pointing in the positive x direction, and the J hat is pointing in the positive y direction. You better know this for the rest of the semester. So here is a handy fact for you, is that any vector in the universe can be written as a linear combination of the standard, and I'm going to abbreviate standard, STD, the standard unit vectors. So write this down. Any vector V can be written as a linear combination of these standard unit vectors, the I and the J, okay? So here's what we're saying. Suppose you have a vector V, and you already know his component form, AB, which could be just numbers, 2, 3, or what have you. If you pull the A out and multiply him with the I hat, essentially the 1, 0 vector, plus whatever B is and multiplied by J hat, that's another way to represent the vector. And if you already took physics, you know this already. In fact, our physics brethren prefer this method of denoting a vector. They rarely use component form, which is unfortunate. I personally hate this version. I'm a big fan of component form. Well, how come? You'll see why soon. It's easy to get confused when you're using I's and J's, okay? And you'll see why. I'll tell you soon. So, quick review. What's the other form of writing a vector that we've studied so far? What's the name of it? Starts with a C. I'll go to chat.
Component form.
Component form. There you go. So that's the angular bracket method that we've done like this. That's called component form. Okay, so you're going to have like a number, a comma, a number. That right there is component form. Okay, but I want you to be comfortable going back and forth between component form and then the linear combo of the unit vectors form. Okay, so let's go do some back and forth. So suppose you had a vector in component form 3, -4. How would you write that using the I hat and the J hat? These unit vectors, these standard unit vectors. Easy. You're just going to go 3 times I hat, and then you could go plus -4, but -4 J hat is more common. And I'm done. It's that easy. How about this component form? Convert that to the linear combo method. Well, you could go 0 times I hat, -2 times J hat, but it's pretty conventional if one of those is 0 to not even bother writing it. So just put -2 J hat. You're done. What about 7, 0? Well, 7 I hat plus 0 J hat. Again, we don't usually use the 0, so you're just going to go 7 I hat and you're done. Okay? So now we're going to do something called resolving a vector into its components. Okay, now David, on Monday, I believe you were asking me about this issue, and I said yes. And I'm going to go over that right now. You asked me something about being able to denote a vector with the angle it's making with the positive x-axis. This is it.
Okay.
Good news, it's pretty easy. It's easy peasy. I'm just going to give you the cute little formulas for it, and boom, you're done. And then we're going to do a big old example, similar to what you'll do in a physics class. So when you resolve a vector into its components, so what do you need to do that? You need its length, the magnitude, and its direction theta, where theta is going to be the angle that the vector makes with the positive x-axis. So just a little picture here, since I've already, where did I draw my picture? Okay, I didn't. So let's just say that, you know, let's say you have a vector here. Let's go with that vector 2, 3 again. Let's say here's your vector 2, 3. This angle that it's making with the positive x-axis, that's the angle we're talking about, okay? So if you're given these two pieces of info, you can actually write your vector in component form. How? How do you get the A and the B, essentially? These are the formulas, so write this down slowly so you get it. The x component is going to be the magnitude multiplied by cosine of the angle. Yes, this is going to be on a quiz. Like, don't even ask me that. Duh. The y component will be found by taking that magnitude again and multiplying it with sine of theta. I'm going to do a couple of examples and then you're going to try one. So let's hang in there. So let's go over why this formula works, okay? So let's say you have a vector here. I'll just do a generic one where the x coordinate is just some x number. and the y coordinate is some y number. It could be 2 or 3 or whatever your favorites are. If you drop an imaginary perpendicular here, I hope you can see that I've got a right triangle going on here. The x coordinate right here will simply be the x component there. So, but what do you have in hand? So the two pieces of info, you don't have the x. You have this length right here, which is the magnitude of v. That's what somebody gave you. And then somebody's going to be nice and give you that angle. That's all you have. And you want to get this x, and you want to get this length here, y. How do you do that? Well, using your knowledge of trig, I hope you remember that cosine is adjacent over hypotenuse. Does anybody remember that from trig? So cosine for us is going to be this leg, which has length of x all over the hypotenuse, but that is the magnitude. They gave that to me already. And when you solve for x by simply multiplying both sides of this equation by the magnitude of v, you'll get that formula right there. And you can do a similar thing for the y using your knowledge of sine. Sine of the angle is opposite over hypotenuse, but the sine of the angle that we're doing there would be this length here, but that's just y all over the hypotenuse, which they gave me, the magnitude of v, and then solve this equation for y, and then you'll get the formula that I have right here. So beautiful. It's pretty easy. There's no brains involved here. We haven't done any calculus yet. As I mentioned on Monday, we're not doing any calculus till the end of next week or the week after that. Because you're not ready, you need to know some solid facts about vectors. Okay, so here's an example. Suppose somebody said, hey, the length is 4, the magnitude is 4. And the angle that this vector makes with the positive x-axis is 30 degrees. Get me the component form. No problem. The x is going to be 4 times cos of 30 degrees. And for those of you who are like, oh man, I forgot what cosine of 30 degrees is. Holy crap. I supplied you with this wonderful trig unit circle diagram just for you. So looking at the trig circle diagram here, what is the cosine of 30 degrees? There's 30 degrees right there. What's the cosine? Talking to you guys.
I'm so scared of saying like radical 3 over 2.
That is correct. That's the
Okay.
cosine. Yay! So that's, we're going to get 4 times square root of 3 halves, and then reduce to lowest terms, I get 2 square root of 3. And then the y component is simply going to be the magnitude times sine of 30 degrees. And the sine of 30 degrees is 1/2. Beautiful. And so you get a 2. Final answer, because they wanted component form here, is you're going to use angular brackets, 2 square root of 3, comma 2. Boom, I'm done. Now, if they ask me for the alternative notation, writing as the linear combination of the standard unit vectors, how would you write that?
4 radical 3 plus 2. I'm sorry, 4 radical 3i.
No. It's
Oh, oops.
number times I hat plus a number times j hat. Remember we did some problems up here where we, in example 4, went from component form to these formats? That's all I'm asking you to do here. So how did we do it?
It's just a 2 radical 3 I hat plus
Yeah.
2 j hat, right?
Correct.
Okay.
That's it. You're done. Now, while we're here, I want to stop for a moment and talk about nonsense. A lot of times when I'm reading a student's paper, and this is probably less likely to happen because my math lab will probably guide you in the right direction and make sure that you give them the form they want. But I want to talk about nonsense notation, because if I see it anywhere on your paper, even if your answer is correct in my math lab, I will dock you points. Listen up, because I'm a stickler for this. Part of the reason why I even have you upload your work is so I can check for proper notation. So one of the weird things that I see students do is they don't get the 2 distinct ways of denoting a vector, component form, and then the other format, which is the linear combo of the standard unit vectors. They start blending the 2 together, like, oh, well, it doesn't matter, whatever. Like I see some crap like this. Let's say the vector really does have components 2, 3. Let's say this is the component form. But I'll see people go like this. Oh, 2i hat, comma, 3j hat. That is crap. If you are using component form, there's no i's and no j's. Okay? So if I see you put anything like that on the paper that you're turning in, even if your answer is correct or what have you, that's when the points are going to go down for yuckiness. What's another silly thing I've seen students do? I'll see them give me the correct linear combo of the standard unit vectors, and everything's beautiful and we're all having a great time. And then all of a sudden they do something stupid, like, oh, I'll put some angular brackets around it just to cover my butt. And then you just went down. Congratulations, that's meaningless crap. That's got nothing to do with nothing. You don't put the brackets around the I when you're using the I hat, J hat notation. So please, folks, the correct way is either this way, this is component form, or if they ask you to write it as a linear combination of the standard unit vectors, you do it like that. So this is the linear combo way. And as I mentioned before, if you've taken physics, they're really a big fan of the linear combo method, okay? Again, I'm not, and I already haven't told you yet why not. We'll get there. Okay, let's talk about you doing one, okay? Real quick, I want you and a buddy to go try to do this. So I'm going to put you in breakout rooms again, okay? And we've got 29 people in the room. So how about, I'll put you in 10 breakout rooms, okay? And then when it says join, go ahead and join, okay? 1, 2, 3. 3 rooms, come on. Okay, you're going to get invited to join, so see ya. Danielle, it doesn't look like you're joining. What's going on? You're in the room, but you need to go join, okay? Otherwise, I'm going to mark you absent. Can you hear me, Danielle?
Hello, Professor.
Yeah.
I went to the restroom. I don't know what happened.
Okay. You're supposed to join breakout rooms, okay? You're being asked to join one right now. Okay, Danielle?
Mhm.
It's breakout room 1. Would you please go ahead and join? You're supposed to do an example. Okay, I won't mark you absent, but I was just about to, okay?
Oh, okay.
All right, be careful. Stay with it. Okay, Dominic, did you not join? Elvis, did you not join?
My Zoom it crashed, and so
Oh,
I had to
no.
reconnect through my phone.
Okay, I'm sorry.
No, yeah, it was Dominic, me, and Aloe, and we left the room, but I guess
Ah.
it just takes us out from Zoom.
Oh, okay. I'm gonna
Yeah.
close all rooms right now.
All right.
Okay? Man, I hate computers. So Dominic, did you understand yesterday's programming lecture?
Yeah, it was interesting. I'm definitely gonna need to practice a little bit just to really get familiar with
Did
it.
you download NetBeans yet?
I did.
Good. Did it work?
It is. I have the page open right in front of me.
Mm-hmm.
NetBeans.
Okay. Did you do a Hello World test run just to see if it worked?
No, not yet. That's why I need to practice.
Okay.
That's
If
why
you
I'm
get stuck,
hesitant to
let me
say
know.
that. What's that?
If you get stuck, let me know.
For sure. I mean, you have those open Friday
Yeah.
meetings.
Yeah.
So
Okay. We're
I'll
gonna
likely join.
we're gonna get back to it. Okay, everybody, how'd we do there? Did we do okay trying to get the component form of this lovely vector?
Feel alive.
Yeah, I think I got it.
Okay.
I think I
So
got it.
what I'm hoping that you got is they gave you the two pieces of information. You got your magnitude and you got the direction. Fantastic. So then what? Well, your x component is simply going to be the magnitude times cos of the angle. And then you go look at your little unit trig circle that I provided for you there. 5 pi thirds, by the way, this for those of you who care about degrees, it is 300 degrees. And that is a half. And so the x component is going to be a 4. And then the y component is, yeah, what the heck is sine of 5 pi thirds? And it turns out it's negative square root of 3/2. And then after reducing, we get that. And then they wanted the component form. So the vector, they're calling it W. I want to see the angular brackets like so. Okay? How many people got this for their answer?
Hey, let's go.
Hey.
Yo.
Success!
Holy.
Yes?
There
They
is
just
hope.
start giving us our
Yeah.
degrees right now. Like
Yes.
I want my bachelor's in engineering like tomorrow in the mail.
Yeah, I'll mail it to you, okay?
Oh, Professor, I have a quick question.
Mm-hmm.
Two, actually. First, are you allowed to express magnitude of vectors with a single absolute value bracket? Or you
The
want the double?
Briggs is. I'm going to encourage you to not do that and do it my way, if
Okay,
you can. I like double bars.
got it. And
Okay.
second, are you like, do you have a preference on how we express like these steps to get the components? Like, do you prefer degrees, cosine, angle? I'm sorry, like in degrees, or do you prefer like cosine, radians, like
Radians
pi?
is a lot of times preferred, but sometimes it's cumbersome, so we'll use degrees or radians depending on the problem. I may go back and forth.
Okay.
Okay, let's go backwards now. What the hell? So what do you mean? Well, in this last few examples, what we did is when somebody gave us two pieces of info, they gave us the magnitude and the direction. We said, oh, no problem. I can resolve it into component form using a formula. But what if we want to go backwards? What if somebody gave us the components, but they wanted the magnitude and the direction? Good news, I already taught you how to get one of those, the magnitude. I gave you the magnitude formula on Monday. So you should already know how to do that, but we'll review. I didn't tell you about the angle, how to get that. So let's talk about that. So here's the magnitude. It's just the sum of the squares of the components where you take the square root of that sum. And then the direction is going to be the arctan of y over x. What? What the heck? Well, if you go back to just here's a generic vector here. Remember we dropped the imaginary perpendicular, so we get a 90-degree angle, and then we have this triangle here, if you already know the X and you already know the Y components, so they gave that to you, and you want to get the magnitude, so you just take the square root of the sum of the squares. But what about this angle here, theta? Well, remember that tangent is opposite over adjacent. Do you remember that from trig? So that's just y over x. But if you take arctan, or tan inverse, same, of both sides of this little formula here, on the left, arctan of tan theta is simply theta, and then theta will be arctan of y over x, okay? So that's the formula, but I'm going to tell you, you better beware. This formula only works perfectly if the vector is in quadrants 1 and 4. And when I say the vector is in quadrant 1 or 4, I mean the tip of it. So if your vector, the tip of it is here in quadrant 1, or the vector is down here where the tip is in quadrant 4, this formula works perfectly. If your vector has its tip over here, you know, in quadrant 2 or quadrant 3, this formula needs a little extra to be added to it. Well, how come? Well, you should have learned in Calc 2 that the range of arctan is negative pi halves to positive pi halves. So anything outside of that interval is not going to be cool. But so if you have a vector whose tip is way out here or way out here, you're not in this interval here. So what are you going to do? You're going to add 180 degrees. Oh, and you'll add 180 if the vector's tip is in quadrants 2 or 3. Otherwise, leave it alone. Okay? Otherwise, the formula works perfectly. Okay, let's do a couple quickie examples. Suppose your vector has components 1, 2. Which quadrant, 1, 2, 3, or 4, is the tip of that vector located in? Quick.
1.
1, very good. So that means when you use the angle formula, you're good to go. Okay, so just go ahead and use that. And now, David, this is where you're going to probably want to use degrees, not radians. Okay, why?
Because it doesn't require radians. That was a bad answer, but I will not use radians.
Well, arctan of 2 is not going to be nice. Like, it's not, I'll give you a hint. Arctan of 1 is actually real easy. Oh, that sucks. Because apparently I don't have some TI stuff on here. So I'll just tell you that when I use my graphing calculator, I get roughly 63.4 degrees, which doesn't translate well to radians, so we'll let it go. Now, what about the magnitude? Well, you know how to do this. Square root of the sum of the squares of the components, I get square root of 5. We're done. Okay, so that's the magnitude, and this is the direction. So I'm done with that problem. Let's do letter B. Similar, the components are -1, +2, but a little different. So which quadrant, 1, 2, 3, or 4, would the tip of this vector be located in?
Oh no.
If you plot the point -1, 2, it's right here. So this vector is over here. You see him? That's quadrant 2. So what does that mean? Your direction, you'll start off like getting your arctan of -2, which again is approximately 63.4 degrees. But do you see that the angle is, you should know right away that that's wrong. Like, I hope that you can look at your picture of this vector that I just drew here and notice that this angle that it's making with the positive x-axis, do you see that this angle, oh, sorry, I got so much mess here. It's a disaster zone. So here's your vector with components -1, 2. This angle here, do you see that that angle is larger than 63? So this is wrong. So you should immediately go, oh, this is not going to work for us, right? Oh, by the way, this should be negative. I blew this, sorry. This should be negative 63.4. Sorry, I wrote it down wrong. So is this angle negative 63.4? No, that would be down here. This angle down here is negative 63.4. So what you're going to need to do to get us back to where we really are is you're going to need to add 180 degrees to get the correct direction for this vector, because he's over there in quadrant 2. So when I whip out my calculator and add 180 to negative 63.4, I get roughly 116.6. Now the magnitude is actually the same, because the square root of the sum of the squares is still going to be square root of 5, like the other guy. Okay? And we're done there. Now I'm going to do a physics example. This is going to knock some of your socks off. So what does this all have to do with real life? And as engineers or math majors or scientists or whatever your major is, you better care about this example. And you'll see it in physics a lot. So most of you have to take physics, including computer science people. So if you focus up on this example, you're going to be good to go, because I'm going to break it down and make it easy for you. But I claim that you have all the knowledge to be able to do this problem. And it's going to be like going for the gold. We're going to use the formulas that we looked at today, like resolving a vector into its components. We're going to use vector sums, and we're going to find magnitudes and find direction. So it's going to be a multi-step problem. Try to stay with it.
It's got a flashback.
So the idea is, and I'll draw you a picture because it's kind of fun. You got a large piece of granite right here, you know, sitting on the ground or whatever, and you're going to want to move it, but it's too hard to move by yourself. So you're going to harness up your horse. And I know a lot of us don't have horses. I don't have horses, but when I was growing up, my best friend would always take me horseback riding, because she always had a horse. And she'd always be really into horses. We used to collect plastic horses, and it was fun times. Anyway, so here's my picture of a horse. Yeah, it's pretty sad. Sorry. So if you hook up the piece of granite to your horse somehow by whatever, let's say your horse is able to pull in this direction. So there's the horse force vector with a magnitude of 1,000 pounds. This 1,000 pounds is actually a magnitude. Okay, and because he's pulling in the same direction as the ground, you can think of the angle as being 0 degrees. Now, you're going to help your horse out, because you don't want your horse to get too taxed. So you're going to stand a little bit off to the side, like here, and you're going to have a rope, and you're going to pull also, but you're not very strong. So you're going to only pull with a force of 200 pounds, so that's another magnitude, and the angle that your rope makes with the horse's rope is 50 degrees. So the $64,000 question that you wanted, the goal, is give the magnitude and direction of the resultant force. Resultant force means you're going to add some force vectors together. Another way of thinking about this is, what's the total force that the granite is feeling? I know granites don't have feelings, but if the granite could feel, what force is he experiencing total between you and the horse pulling on it? That's the question. Now, what you're going to do when you're thinking like a physics person is you're going to overlay a rectangular coordinate system on top of this picture. And you are the boss. So you want to be, when you overlay it on top, you want to be a smart rat and put the origin in a smart spot. So if I were to overlay the rectangular coordinate system on top of this big old picture, I would put the origin right there where the two ropes meet. And then the positive x-axis here is in the direction of my horsey, and then the vertical is just straight up. So there's my rectangular coordinate system. So over here, I'll redraw it. Here's x, here's y. So because the horse is pulling with 1,000 pounds of force, and that's the magnitude, right here at the 1,000 on the x-axis, this is not drawn to scale, the force vector of the horse, which, what did I call? I'll call that F1 in my notes, is simply there. And then we'll call your force F2. Your force is not going to be as long because your magnitude is only 200, and you're making an angle of 50 degrees with the horizontal. So what we're trying to find is, we want to try to find F1 plus F2, and then take the magnitude of F1 plus F2, because that's going to give us the overall force. And then we also need to find the angle that the sum is making. Now, using the parallelogram rule, and thinking of those two force vectors we see there as adjacent sides of a parallelogram, the resultant force, I'm going to try to draw it, is the diagonal of this parallelogram. So this red vector is our answer. That's him. That's the F1 plus F2 vector. And I hope you can see that he's making a very small angle with the positive x-axis. It's definitely less than 50 degrees, I'll tell you that right now. So one of the goals is we're going to get the magnitude of the sum, and then we're going to find the direction, which is going to be some angle. So these are the two answers we're looking for, and then we'll be done with the problem. But it's going to take a little bit of time, so stay with me on this. The first thing we're going to do is you're going to take the F1 vector, that's this one that's lying horizontal on the x-axis, and you're going to try and figure out what his component form is. Now, I claim it's the obvious. You don't even need to use any of those formulas we just used, because you can clearly see that the tip of the vector, because it's located at the point 1000, the component form is simply going to be angular brackets 1000, comma 0. Now, if you didn't know that, you're like, well, how did you know that? You could have used the formula that we just did on the previous pages and take the magnitude and multiply it by cosine of the angle for the x component. The y component, take the magnitude and simply multiply it by sine of the angle, where the angle that it's making is 0 with the positive x-axis. Now, cosine of 0 is 1, so 1000 times 1 is 1000, and sine of 0 is 0, so the y component for F1 is clearly 0. Now, what about the F2 vector? That's you trying to pull and help out your horse. So what are his components? And there are only two pieces of info we know about you and your force. You were given the magnitude, which is 200, and you were given the angle, 50 degrees. So no problem. Now you are going to use the formula to get your component form. 200 multiplied by cos of 50 degrees is the x component, and 200 times sine of 50 degrees is the y component. And this is where you're going to want to whip out your calculator, because those are not nice. So your F2 vector, and I'll put approximately because we'll round off some, is, and I won't round off a lot till the very end. So try to keep a lot of precision here, like lots of decimal points, until the very end. Otherwise, you'll propagate a rounding error. So I'm going to use 4 decimal places. So now I can do F1 plus F2. So what is that going to be? That's going to be a vector. And so you're just going to take the x component for the F1 vector and add it to the x component of the second vector, and that will give me, after I add this together, 1128.5575. And then when I add the y components together, and 0 plus anything is obviously the anything, and there is the component form for your resultant vector. Yay, success, but I'll only give you partial credit if you get this far. Keep going. I want the magnitude. How do you get it? You're going to take the square root of the sum of the squares of the components. And yes, you're going to need a calculator to do this. Yes, it's crazy. And it's approximately, I'm going to round to the nearest pound. It is pounds for units. It's 1,100 pounds. That's approximately the overall magnitude. And that's what the overall feeling that the rock is feeling, that the total force that he's getting pulled with, 1,100 pounds. Okay? What's the angle? Well, clearly from our picture, this resultant vector is in quadrant 1. Good news, because when we use the arctan formula here, we don't have to add 180 degrees. We'll just use whatever our calculator tells us. So we're going to take the arctan of this quotient. You know, it's a weird number. And I'm going to round to the nearest whole degree. I get approximately 8 degrees. So that's the angle of the resultant vector here, and that looks like it's about right. And I'm done with this problem. So what should you take away from this? That vectors in the real world help a lot. And if you're an engineer, especially if you're a mechanical engineer, you're probably going to take an engineering course here at Southwestern College called statics, and you better know all this stuff. Like, don't embarrass me and go, oh, I didn't learn that stuff, when you take that class next semester or whenever you take it. Because, yeah, you did. Or if you go to physics and they make you do this, okay? I'm going to open it up for questions right now. Any questions, comments?
Please take Calc 3 before you take Physics 1.
Yes.
Could you scroll back up to just right there, please?
No problem.
Or to the angle.
The answer for the angle right there?
Yes.
All good? Now, folks, this is like a word problem. And, you know, I know students, the minute they see a word problem, they poop their pants and then their brain shuts down. But in this class, you won't have tons of word problems per se, but a lot of times you are going to have to do a setup. It's not going to be like a Calc 2, like, okay, here's an integral, go use U sub and integrated integration by parts. You might have to do some thinking and work to do a setup before you actually do any mathematics. So that's part of this class. I think that makes the class fun. Question? Are you guys talking in the back there? I hear somebody asking a question. Okay, so Nick, you think this stuff, okay. Yeah, this stuff is easy if you have a Calc 3 instructor to do it. For those of you who are taking physics right now, drop, get out. Take this class first and take your physics next semester if you want to ace your physics. Otherwise, prepare to die. And trust me, I've seen people do that. I even have some of my Calc 2 students who Monday I had to tell them, do not take Physics 1 right now. What the heck are you thinking? Because they're going to pretend that you already know everything about vectors, or they'll cover it in 5 seconds flat. And we got a lot to do with vectors. You're not even near. You're rookies. So let's do another problem that's a word problem, where this is about static equilibrium, okay? Take a look at this little picture here, this little diagram. Static means nothing's moving. So we're going to have some force vectors here, and we're going to add some force vectors up. But this time, instead of just adding them together and getting the result, we're actually going to set the sum equal to 0. Because nothing is moving here, in the previous problem, the granite was moving. Here, nothing's moving. It's just static. So that's when you add up all the force vectors and set it equal to the 0 vector. And then you're going to use equality of vectors. So this problem is going to take some breakdown. So first I'm going to draw where the force vectors are. Then we're going to overlay an XY coordinate system on top of it. Then we're going to resolve all 3 force vectors into component form. Then we'll sum them up, setting them equal to 0. And then we're going to end up having to solve a 2-equation, 2 unknown linear system. This is a multi-step problem. I hope you had a lot of coffee, because it's going to be a nightmare. Here we go. Yes, it's going to be in my math lab. Don't even ask me that. Like, yeah. Don't fall asleep. Okay, so this cable right here, cable 1, is experiencing some tension. Like it's trying to hold up this 500-pound weight without, you know, breaking. So we're going to draw this. I'm going to call it U, say. Actually, I'm going to call him V. Sorry, I'll stick to my notes. That'll be the vector V. This cable here is struggling and having to experience some tension here. It's a force vector. We'll call him U. There's a third force here that's pointing down. I'll call that F. That's the force of the 500 pounds, straight down. So the static equilibrium means no movement. And it means all forces add to 0. That's what that means. And this is an application of vectors. So when when students go, oh, what's an application of this? And then I tell them, and they go, oh, it involves a word problem, I'm out. It's like, well, you asked me for an application. My dad has a saying, if you can't stand the answer, don't ask the question. Okay, so here's the claim. U plus V plus F better equal the 0 vector, because nothing's moving. So you got to get U and V and F in component form. So this is what I need to do right now. I need to get the 2 components for U, the 2 components for V, add it to the 2 components for F, and that's going to equal the 0 vector, which has component 0, 0. So that's kind of, I have a lot of unknowns right here that I got to go get. It's like, oh man, really? Yeah. Well, they didn't give me any information. Yeah, not much. It looks like you can't even do the problem, but we're going to work with it, and I claim there is enough info. So let's do the F vector first. Well, first let me overlay the X and Y coordinate system. So I claim that the smart rat would lay the X-axis down right there and the y-axis right there. That's the smart way to roll. So if you do that, then your U is like that, your V is over here, and your F is pointing straight down like so. Okay, not necessarily drawn to scale, but that's what we're looking at. Okay, so look at the F vector. They gave you a magnitude, which means that since this is 500 in length, it should be obvious that the angle it's making with the x-axis is negative pi halves or negative 90 degrees here. And I don't even have to do any work to get component form. I claim that the F vector is going to simply be 0, negative 500. Do you believe it? If you don't, and you go, well, I want to see proof, like give me that formula you did on a previous couple pages. Okay, 500 times cos of negative 90 degrees, 500 times sine of negative 90 degrees. How about them apples? And since cos of negative 90 is 0, that's why you're going to get a 0 component. Sine of negative 90 is negative 1, and so 500 times negative 1 is going to give you negative 500. So there's your component form for F, yay us. Now, how about the U and V? They told us that there's some angles here, but they didn't give us the angles we want. We got 30 here and 70 here. From geometry, when you have two parallels cut by a transversal, I hope that you can see from geometry this angle here is 30 degrees. Okay, and then that means that this angle here, which is the angle that we're going to use for V, is going to be what? Anybody have an idea?
80.
70.
Well, okay, this angle right here is 70, like on the other side, so I'll use color here.
Oh, I thought that's what
This
you were asking
angle
for.
here, this is not drawn to scale, okay? This is 70 right there. So what would this angle be right here?
130?
It would be 130, yeah. Well, excuse me, 180 minus 70. What's 180 minus 70? 110, right. So what am I saying? If we're going to break U down into his component form, we have an unknown, his magnitude. I don't know what it is. In fact, that's one of the things we have to find. Whatever his magnitude is times cos of 30 degrees will be his x component. And then whatever that magnitude is times sine of 30 degrees will be his y component. Okay, now if you do this knowing what cosine and sine are, I'm actually going to use decimals. This is going to be like 0.866 times that magnitude that I wish I knew. And then this is going to be, what is it? 0.5 times the magnitude of U. Okay, so we'll stick with that. And now we're going to break down the V cable into his components. So we don't know what his magnitude is. That's going to be one of the unknowns. And the angle he's making with the positive x-axis is, remember, 180 minus 70, which is 110. Like that. Okay, yeah, and you're going to get some yucky numbers here. It's pretty gross, all right? So I'll leave it like that for now. Now, what are we trying to say here? We're trying to add all three of these vectors together and set them equal to the 0 vector. That's the goal. So in order to create this vector on the left-hand side, which is one big old vector, you're going to add U, that's this guy here, or you could use this guy, I don't care, plus V plus F. So when you go U plus V plus F, let's get it. You're going to add all of the x components together, so you're going to basically have U times cos 30 plus magnitude of V times cos 110 plus 0, because the force vector had a 0 for an x component, comma, now you're going to add up everybody's y components. You're going to go, okay, U's magnitude times sine of 30 plus V's magnitude times sine of 110 plus negative 500. Okay? And that has to equal the 0 vector. This is where you're finally going to use equality of vectors. Again, remember I told you that's going to save your butt? Here it is. the vector here has to equal this 0 vector. What does that mean? The components have to match. So this has to match a 0. So I'm going to write that down. The y component has to equal 0. So I'm going to write that down. I claim this is a 2-equation, 2-unknown linear system. You should be able to solve it for magnitude of the unknowns. You know, normally when you do a beginning algebra problem that's linear, you're probably going, that doesn't look easy because I don't like it. Okay, calm down. Normally when you're doing a linear system, usually you see like the unknowns be x and y. You know, like you've probably seen a linear system like, oh, 2x minus y equals 4, and x plus y equals 7, or something like that. You've done stuff like that, right? That's what this is. But it's instead of x's and y's, you've got magnitude of u and magnitude of v, so it looks a little bit scarier. But I claim you can use substitution or elimination, your choice. I'm going to use matrices. When I use matrices and I put all of the, like this is 0.866, this is negative 0.342, and then this guy goes 0 here. This guy goes, no, I don't want to do that. Go away. Sorry about that. This is 0.5, this is 0.9397, 500. You could do it with matrices also. If you're confused by now, don't worry about it. I don't have time to solve this. I'm just going to skip to it. I'll give you the answer. So what I would do also is I would move this minus 500 to the other side if you're going to add the two equations together and use either elimination or substitution. But the magnitude for you, it's approximate, is 173.6, and the units are pounds. And the magnitude for the other cable is approximately 439.7 pounds. And that's kind of interesting to me because if you look at the picture, those cables have to withstand, not, you know, together, they have to be able to handle the 500 pounds there. So it looks like the second cable is taking on more of the load there. Maybe it's going to break. Who knows? Okay. So that's that example, and questions about this example. Anybody seen anything like this before, maybe?
Could you tell me how you got 110 degrees?
Yeah, sure. Okay, let's look at the original picture, and let me delete some of the yuckiness here. So if you remember from maybe, or maybe you don't, that's fine also. When you have two parallel lines, like here and here, cut by a transversal, this 70 degrees is also going to show up on the other side of that line. So over here is 70 degrees. Can you see that, Vanessa?
Yes.
You with me so far?
Uh-huh.
Cool. So would you agree that if I started over here on the positive x-axis and went all the way around, that's 180?
Yes.
Okay. But I don't want to go all the way around. I want to just find the angle of this cable here. So I'm just going to need this angle here, going from here to here, right? And I know that this unknown angle, I'll just call it theta for now, theta plus 70 degrees has to equal 180 degrees total, yes?
Yes.
Okay, solve for theta. What happens?
Okay, I get it.
So when you subtract 70 from both sides, you see how you got the 110?
Yeah.
Cool.
Okay. Thank you.
You're welcome. Any other questions on this? You got time?
Can you explain how you got those values in the matrices at the end?
Yeah, when I use matrices, and if you haven't taken Math 254, you might be confused.
Yes.
But cos of 30, when I just round it on your calculator, it's 0.866. Type it up, you'll see.
And we don't need to add the, what about the vectors, u
These
and
magnitudes, you don't throw
sorry,
those
the
into a matrix if you're going to use the matrix method for solving a system of equations. In fact, I'm sorry I even brought this up because I think this is confusing. So a better way is just use your algebra stuff. So in other words, like what if I took this equation and I solved it for, say, magnitude of u? How would I do that? I would subtract this term from both sides and divide both sides by the cos of 30 degrees. You with me?
Yes.
Then I would substitute this puppy into the other equation right here. You with me?
Yes.
So have you seen this method of substitution before?
Yeah, it's very extreme, but I've seen it.
Yeah, it's pretty gross.
I see
But
why
if
you'd
I
use the
substitute
matrix.
that there, then I hope you see that the second equation has, the only unknown that the second equation has is this magnitude of v. You see he's the magnitude, that's the unknown.
Yes, I see that.
And now you can use this and your calculator, of course, to solve for v. You with me?
Yeah, because you have a lot more real numbers that you could
Yeah,
calculate
you
now.
just you factor out the v and then do a bunch of arithmetic and boom, you got your magnitude of v. And then use whatever you got here to plug back into since you had already solved for u, and then you'll be able to get your u.
I understand why you would use the matrix method. I'm sorry that I made you erase that, but I do understand why a lot better now.
Okay, that's cool. All right, we have a little bit more time to do questions, and I may just allude to something else real quick before I let you go, because just think of it as free education. Yes, you're going to use your calculator and matrices on a test, Emily, and if you do, I'd want you to write down on your uploaded work the matrix that you're using to punch up into your calculator, which menu item off your calculator you used, and you're probably going to use the RREF, row reduced echelon form, to get your result. As long as you put those steps down on your paper, I'm good. Does that answer your question, Emily?
Yes, it does. Thank you.
Okay, you're welcome. Otherwise, the rest of you, if you don't understand matrices, just go do it the hard way. Let's just briefly look at the 3D system and then I'll let you go. If you have to go right now to another class, I'll upload the recording this afternoon or for sure by tomorrow. Go watch it. Let's just talk about 3D real quick because we need to, because I'm a little behind here. Because, oh boy, we'll have a lot of fun on Friday. Here is a picture of 3 dimensions, okay? And it's important that you get that when you have 3 dimensions, you're going to have 3 axes. You're going to have the x-axis, which is going to be pointed to the left. You'll have the y-axis, which is kind of pointed at us, like out of the paper. And the z-axis will be pointed vertically in this class. I just want to say in your physics class, I think they do it like this. They go x, y, and then z is like pointed out of the paper or something like this. If I see you do it like that anywhere in this class, and yes, I'm going to ask you to draw some things in 3D. I'm going to just mark you wrong up the wazooby there. Do not do it like the physics people do. They have their head turned on, put on upside down or sideways or something. So in math classes and in every calculus book you'll open, this is the way we roll, where x is going to the left, y is kind of going to the right, and z is going up. And yes, it matters, because we want to get oriented here. Instead of 4 quadrants, you're going to have 8 octants. And I don't want you to memorize all 8, because I don't even know what the hell all 8 are. I do want you to know octant 1. So there's 8 octants. And octant number 1 is the important one. That's the one where it's kind of coming out of the paper. It's sort of right here, where x, y, and z all take on positive values. So that's kind of cool. And then the other thing you're noticing in this picture, you're noticing these 3 colorful planes. You better know them. The blue one is the XY plane. What happens in the XY plane? Z is automatically understood to be 0 when you're sitting in the XY plane. If you're in the XZ plane, that's sort of the plane that the X and Z axes make when you kind of put them together, it's understood that Y is zeroed out. And finally, in the last plane, that's this sort of beige looking one, that's the, no, that's the, sorry, the beige is the XZ plane. The green one, the green plane here is the YZ plane. Sorry, I miswrote that. So this plane right here is the YZ plane. This plane over here is the XZ. So when you're in the YZ plane, it's understood that X is zeroed out, okay? So it's good for you to know the three-chorded planes and the axes orientation and about octants, so that when we get into looking at points and drawing vectors in 3D, you won't get too confused, okay? So we'll start that on Friday, looking at plotting points in 3D and looking at vectors in 3D. So don't miss Friday's class. I noticed a few people were absent today. Maybe they couldn't wake up. But it's tough to watch a video and not be able to ask questions. You guys know. So I'm going to stop there. See you later. Have a good day. Don't forget, you have some deadlines tonight. You better upload your take-home quiz. It's real easy. It's mostly essay. Bye.
All right, bye. Thank you.
Hey, Professor,
Yes.
can you go back to the problem that we were doing?
Yes, I can. Right there?
Yeah, a little bit more. Yeah, right there. How did you get the values for U?
You mean the components here for you?
Yeah.
Okay. Do you get how I did this line right here? I just used magnitude times the angle. Magnitude times the angle. Hello?
Oh, magnitude times the angle.
Magnitude times cosine of the angle. Magnitude times sine of the angle. Hello?
Yeah.